Somebody tell me what it was that Thomson discovered about the atom. Say again? Electrons. Great. So that's the first thing I would say. So anything else? How about that it is charged? Anything else that he said that's still accurate? It was an inference he made from this discovery. Wait, say that again.
That you use the simple full numbers to.
No, total wrong guy. Yeah, wrong guy. Does that make sense? I have an object that's not charged, and then I make a part of it come off, and I see that that part is charged. So what does that infer about the object that's left behind, the portion of the object that's left behind? That has to be charged and has to have the opposite charge of the thing that came off, because when it goes back on, again, the two things have no charge. Okay, what was it that Rutherford discovered about the atom? Nucleus. Small, dense,
positive charge.
Massive. He confirmed positive charge.
And he also showed that it wasn't the whole atom was positive with just negative emittance for each of them.
Right. That's the nucleus itself is the reasoning behind that. Why am I saying this? Why am I saying massive? Yeah, when we say massive, I'm not saying that this is like a huge chunk of something or other, but relative to the atom, it is the most massive part of the atom. So even though the atom itself is incredibly small in its mass, this is the most massive portion of it. Almost all of the mass is there. Effectively, when an electron leaves the mass, we don't analyze a mass change because that mass that left was so small. Okay, how about Sadi?
Discovered protons.
And it's a +1 equal to the -1 of. So he works with Rutherford and figures out that the nucleus isn't just a chunk of positiveness. He figures out that it's formed by individual protons with a +1 positive charge, and that +1 positive charge equals the -1 charge that's on the electron, which is why the charges cancel out when the atom is whole. And how about Rutherford? Or sorry, how about Chadwick? Neutron. 33 years later. I don't know, it's not up here, but do we remember what the neutron purpose was? Magnet? No. What are you saying?
Like if you have two protons, they need something in order to connect, so they have the neutron.
It's not to connect them. It's actually to keep them from being connected. So, what do you want to call that? When you got two things and you don't want those two things to touch, what do you put in between them? A buffer or an insulator. So it keeps them from having to actually be on top of each other. I'm sure lots of you put Christmas lights or Christmas ornaments away, not too distant past. You didn't put the two glass ornaments right next to each other, right? You put like a piece of styrofoam in there or cloth or something or other so they didn't run into each other. So X All right. Define and give an example. So isotope. What do you got there? Atom with specific number of neutrons. And examples would be like carbon with a mass of 12 and carbon with a mass of 14. They're both carbon, so because there's a C there, that's telling you that that thing has 6 protons in its nucleus. But then the number to the right is its mass, and so the mass isn't the same. So the carbon that's mass is 14 has 8 neutrons in it, and then the carbon with a mass of 12 only has 6. So same atom, different numbers of neutrons. The allotrope.
It's the same atoms, different composition, like those.
Same atom in different molecule, only with itself. And examples, easy, O2 and O3. They're definitely different atoms, or different molecules, but they have the exact same atoms inside of them. Diatomic?
That's paired with itself.
So those 7. You can't find those 7 atoms by themselves. So there aren't any I's floating around or BR's floating around. They have to come as pairs if they're in their atomic form, atom form. Okay, so we've got these four rows here of these different isotopes. The first one is Be, so that's beryllium. And beryllium, since it says Be, how many protons does it have? 4. And if it's an atom, it's got 4 protons, it's got 4 electrons. So why is this mass number 10? It's that neutron number plus that proton number to make it 10. All right, so the next one I've got an atomic mass of 82. So anything that has, or sorry, atomic number of 82. Anything that has 82 protons in it is what? Lead. Symbol for lead is Pb. It's got 82 protons, so it's got 82 electrons, and so then its neutron number, if this particular lead has a mass of 207, it's going to be what? 125? So this 82 number plus this 125 number equals my 207 number. Is that right? Yeah. 207, yeah. All right, so OS is osmium. Does anybody know anything about osmium? No. All right. What element number is it? 76? And so if it's got 76 protons, it's got 76 electrons. And if this osmium's mass is 190, then the number of proton or neutrons that it has is 114. Is that right? 114. All right, and so the last one here is radium. So that's Ra, and that's 88. Is that right? Or is it 86? 88? 88. So it has 88 electrons. And since this radium has 138 neutrons, then it's going to have 226 for its total mass. Okay. All right, so according to Dalton, what happens during a chemical reaction?
Atoms are fine, separated by rearranged.
Okay, that's good. How come Dalton's happy to know the chemical formula for water is H2O? So two things here. Let's start with simple. Simple whole number ratios of atoms. How about just ratio of atoms? And fixed. He's happy that it's just two H's and an O, and he's happy to know that every single time I look and I find a water molecule, that it's always two H's and an O. And if I change that, then I'm not looking at water. How about this last one about matters mostly empty space?
Electron cloud, just like electrons, supposed to just like electrons spinning around.
So I have this huge space that's filled with where the electrons are going to be found, and in the center I have this dot. And that dot is where, like we said earlier, most of the mass of the atom is. So all that space where the electron is like the space that's around our planet. There's almost nothing around us, and every once in a while there's an object. If an asteroid or meteor or some other celestial body were to shoot through our solar system, what are the chances that it hits something? Pretty slim. There's all the specks of mass are really, really spread out. There's a bunch of empty space. So all of our atoms are these little specks of mass surrounded by a bunch of empty space, and then there's empty space in between the next atom. So it's a mass, empty space, empty space, empty space, and a little bit of mass. So most of what you are is empty space. Another way you could do it is atom is 10 to the negative 10th meters in size, and nucleus is 10 to the negative 15th meters in size. So we're talking 5 orders of magnitude here, difference between the size of the atom and the size of the nucleus. Okay.